Up to this point, we have dealt with equations that just had one variable in them and one solution. For example, 3x plus 4 equals 13. In this video, I will begin to discuss equations that have two different variables and, because of that, more than one possible set of answers. Consider the equation y equals x plus 3. In this equation, it is possible for x and y to be all different values. For instance, if x equals 1, then y equals 4. If x equals 2, then y equals 5. One answer is dependent on what the other answer is, and there are an infinite number of answers. Since mathematicians like to give all possible answers to a problem, it would not be possible to list all the answers. Thus, we use the idea of graphs to show all the possible answers. One way to show all the possible answers is to put the answers on a graph. We can start by making a t-chart that lists some possible answers. So I'm going to make a t-chart over here to the left, and I'm going to give the headings x and y. We know in this particular equation right here that if x is equal to 0, then y is equal to 3. If x is equal to 1, y is equal to 4. If x is equal to 2, y is equal to 5. I could also go with some negative values for x. If x is equal to negative 1, y is equal to 2. If x is equal to negative 2, y is equal to 1. If x is equal to negative 3, then y is equal to 0. So what I've done is I've listed a lot of the different possibilities for x and y. Now remember, you could also have fractions. I could say something like, if x is equal to 1.5, then y is equal to 4.5. There are an infinite number of answers that I could have for this particular equation. Here I took the solutions we found in the t-chart and plotted those points on the graph. You can see that right here is the point 0,3. Here's the point 1,4. Here is the point negative 1, 2. And so forth. So I have all those points plotted. Notice that one of the points I actually do not have plotted right now, 1 1/2, 4 1/2. I could plot that particular dot. It would be about right here. Okay? And that leads to something very important that I have written down over here to the right. First of all, because there are arrows on either side of the line, it indicates that the line continues forever in both directions. Every coordinate pair on the line, shown or not shown, is a solution for the equation. So a mathematician, by doing this, is showing all the different possible answers for this equation, y equals x plus 3, by putting that on a Cartesian coordinate grid. All of the equations we will deal with in this section are called first-degree equations. They are first-degree equations because the variables are always to the first degree, or the first power. They have an understood exponent of 1 with them. All first-degree equations, when graphed, form a straight line, and that is a very important point for this discussion. Here's another example of a linear equation. Y equals 6x subtract 5. This equation, as well as the first equation we did, y equals x plus 3, is a certain type of linear equation known as a slope-intercept equation. It is a slope-intercept equation because the equation is solved for y. In other words, one side of the equation is just y. I have y equals. Notice I don't have 2y or anything else. I just have y equals on one side of the equation. Here's another example of another slope-intercept equation. Just like we did previously, we can graph this equation if we wanted to by setting up a table of values for x and y and then going through and plotting the points. So here's my t-chart with x and y as the headings. If I wanted to, I could say, well, x is equal to 0. If x is equal to 0, putting 0 in for x, I would get y is equal to 3. And you can see that I have plotted that particular point right here, the point 0, 3. If x is equal to 1, then I get y is equal to 5. And once again, I've gone through and I've plotted that particular point. And if x is equal to 2, 2 times 2 is 4, plus the 3 gives me 7. And I've plotted that particular point. And then I went ahead and I drew my straight line to show the line for the equation y equals 2x plus 3. Notice once again that I put arrows on either end indicating that there are all sorts of possible answers for that. I just did not list them all in my t-chart. However, there's another way to graph slope-intercept equations that is really faster, especially when the equations are not as easy. Here I have redrawn the graph that we just finished below. Notice that the constant in this equation, 3, is also where the line crosses the y-axis. And I'm going to start right here. I'm going to put a dot at 3 on the y-axis. This is true because when x is equal to 0, all I'm left with is y is equal to 3. So I always start by plotting this constant point on the y-axis. Next, notice what the number is in front of the x. It is a 2. This is the slope of this particular equation. In other words, being a slope of 2, I could rewrite it as 2 over 1, which means that in order to get from one point to another point, I am going to go up 2, and then I'm going to go over 1, and then I'm going to go through and I'm going to plot another point. If I wanted to, I could go up 2 more and over 1 again and plot another point. And then I can just go through and I can draw my straight line for this. This was a pretty easy way of going through and finding points without setting up my t-chart. Now once again, we talked when we were talking about slope. Remember, this line has a positive slope because to get from one point to another, you go in a positive direction and another positive direction. The reason that this is called a slope-intercept equation is because the line has the slope of the number before the x. Once again, it has the slope of 2. And it crosses the y-axis at the constant. In this case, it is a plus 3, which is why we call this the slope-intercept form of the equation. So there are really 3 different steps that I follow when graphing slope-intercept equations. First of all, I take a look at the constant. The constant in this particular case is 5. And what I'm going to do is I'm going to put a point on the on the y-axis where 5 is located. Next, I'm looking at the number before the variable. In this case, it's a negative 2/3. That number is the slope. So I am going to go down 2, 1, 2, and over 3, 1, 2, 3, and I am going to put another point. I can find a third point by using this idea of slope again. From the point that I just created, I'm going to go down 2, 1, 2, and over 3 again, 1, 2, 3, and I'm going to put another point. Then all I have to do is I need to go through and just draw my line. And once again, remember to put arrows on either end to indicate that that line goes on forever and ever. Now, if I want to, I can certainly go through and give the coordinates of each of these points. This is the point 0, 5. This is the point 3, 3. And this is the point 6, 1. So if I wanted to check, I could certainly put those 3 points into a t-chart with 0, 5, 3, 3, and 6, 1, and put each one of these pairs of points back into the original equation and make sure that it is a true equation. And I will let you go through and do the math, but you will see that all three of these points do work. So that is the line for this particular equation. One difficulty some people have with using this method is being able to identify the y-intercept and the slope by looking at an equation. Below are some equations written in slope-intercept form with their slopes and y-intercepts noted. So you can see I have y equals 4x minus 3. The y-intercept is a negative 3. It's not a positive 3, it's a negative 3 because of that subtraction sign in front of the 3. And the slope would be 4 over 1 because I could write that number 4 as a fraction, 4 over 1. In y equals 1/2 x plus 5, the y-intercept is a positive 5 and the slope is 1/2. The third one that I have here, I've also graphed. Y equals negative x plus 2. And the y-intercept in this particular case is a plus 2. So when I graph that, you can see that I started by putting a dot at positive 2 on the y-axis. It says that the slope in this particular case is a negative 1 because there's an understood 1 in front of that x. So the slope is a negative 1 over 1. So to get from my point that I've already plotted to another point, I could go down 1 and over 1 to the right. And I could plot another point. And I could continue going down 1 and over 1 to the right. At the same time, if I wanted to, I could go up 1. If I go up 1, that's a positive 1. And if I go to the left, that is a negative 1. But remember, a positive divided by a negative is still equal to a negative 1. So I've gone through and graphed that one as well. If you can get a piece of graph paper, here's an equation that I would like you to graph. Once again, please pause this, graph it, and then turn this back on again so you can check your graph with my graph. Okay, hopefully you've had time to go through and graph this. Following those three steps, the very first thing I'm going to do is I am going to take a look at my constant, which is also my y-intercept. My y-intercept is a negative 3, so I'm going to put a dot at negative 3. My slope is the number that comes right before the x. In this case, it is 1/2. So to get to the next point, I am going to go up 1 and over 2. If I do that, I'm going to be able to put a dot right here at the point 2, negative 2. If I want to get another point, I'm going to go up another 1, I'm going to go over 2, and I'm going to be able to put another dot. So now I have 3 dots, and I could go through and I could connect those dots. Now remember, if I want to go in the other direction, I could go down 1 and over 2, because I'm still, when I go down, I'm going a negative direction down. If I go to the left, I'm going a negative direction also, but a negative divided by a negative does give me a positive, so I still have a slope of 1/2. Now I could go through and I could connect those, and now I have drawn that line, y equals 1/2 x minus 3. Being able to graph lines written in slope-intercept form is a very important part of this course. If you want more practice, please look for the practice activities I have included in this module.